Welcome to Angel Lizzle's YouTube channel, where we make geometry great. Right. Today we're going to be going over 10.3, areas of regular polygons, continuing our ability to find the area of everything in geometry. So we're going to discuss this somewhat similar to discussing circles. The center of our polygon is the center of the circle that is circumscribed about the polygon. So the center of the circumscribed circle about the polygon. Right. So right here. All right. Okay, here's our center. Center of that circle. Remember what circumscribed means. A circle is around the polygon and touches at each of the vertices. The radius of the polygon is simply the radius of that circle. The radius of the circle circumscribed about the polygon. So in this case, from our center to the end, there's our radius. Pull that off. You guys have one more in your notes, right? It's the side of the polygon. I think that's self-evident. Next is and a new word you've probably never heard of, the apothem of the polygon, not the cute animal that hangs upside down from a tree. The apothem is the perpendicular length from the center of the polygon to the side. And we're going to use baby A to denote the apothem, that perpendicular length from the side to the center. And the last thing we need to define is the central angle of the polygon. So the angle with a vertex, the center of the polygon. And in order to calculate the areas, we don't need the central angle, but what we do need the central angle for is to find these lengths. The apothem and the radius, and sometimes the side of the regular polygon. All right, so our central angle looks like this. If it's a regular polygon, they're all going to be equal. Right, so a central angle there's the central angle right here. There's a central angle. And to find the measure of that central angle, we can take 360, which is all the way around, right? And divide it by n, the number of sides. And this works because we're calculating the area of regular polygons, which means all sides and all interior angles are equal. So In this case, we have 1, 2, 3, 4, 5, 6, a hexagon. So each of those central angles is going to be 60 degrees. That's 60 degrees, 60 degrees, and all the way around. 60 degrees, those central angles. All right, our first example. We want to find the measure of the angles of the triangle in the radius and the apothem of the regular hexagon that has a side length of 8 inches. All right. I'm going to go a step further and use the idea of triangles. Go ahead and figure out the area of this hexagon. I'm going to take this guy, move it over here. So I'm going to have some space to work. All right, so first thing I want to do, we did this up here. I want to find the central angle. So the central angle (360) divided by 6, 60 degrees. Right. So this right here, 60 degrees. And while I'm at it, why don't I find the perimeter of this hexagon? Since it's regular and I have the side length, these are all 8. There's 6 of them. So 6 times 8, 48 inches. Next, I want to find the radius and the apothem. So what I'm going to do is, this is 60, and I have a perpendicular bisector here. I want to find this radius and the apothem. All right? And we'll go ahead and take this aside. This over here. Go ahead and blow this up so we can take a better look at it. So there's my apothem. There's my radius. All right, so the first thing, I want to find this angle up here. So half of 60 is 30 degrees. And since our apothem bisects the side of our regular polygon and creates a right triangle as well, we know that this is half of the side length. That's full. So we hopefully can recognize this as our special right triangle. Remember our 30, 60, 90 triangles where we had x, 2x, and x square root 3. Okay. And we have to determine whether or not I have the short leg, hypotenuse, or long leg. In this case, across from the 30, this is my short leg. So to find the hypotenuse, I can double it. I end up with 4 square root 3. My bad, it's not 4 square root 3, that's the other one. We're going to double it, and we end up with 8 as the radius. And then this, the middle side, is 4 square root 3. Get those mixed up. So our radius here is 8 as well. And our apothem is 4 times the square root of 3. So what do we notice about the hexagon, the regular hexagon, that makes it so beautiful? It is made up of 6 equilateral triangles. So 6 equilateral triangles. So could I figure out the area of one of these equilateral triangles? Sure, that apothem that we just solved for, that's the height of the equilateral triangle. Right? So my height is 4 root 3. The base is 8. So what's going to be the area? The area of one of these triangles is 1/2 base times height. So the area of one of these triangles is 4 times 4 root 3. Or 16 root 3. And then the area of the entire hexagon, so that's the area of the triangle right there. The area of our hexagon is 6 times 16. We're getting 96 root 3. And don't forget to put appropriate units, inches squared. So looking at equilateral triangles to find the area of a regular hexagon. This only works with hexagons. And hexagons the only regular polygon that is made up of all equilateral triangles. All right, so since all the side lengths are the same, and we know an equilateral triangle has angle measures of 60, 60, 60, instead of having a formula where we have the area of a triangle as 1/2 base times height, it would be convenient if we had the side length alone, right, to be able to find the area of an equilateral triangle with just one thing, the side length, instead of a base and height. So let's see how we can go ahead and look at this. So let's go ahead and get an equilateral triangle out here. Best we can. All right, so we have our equilateral triangle. And let's make this side length S. And we know all equilateral triangles have internal angles of 60. Right? These are all 60. So let's use this formula for the area of a triangle. Go ahead and calculate or compute an area formula that just relates to the side length. So this is a 30, 60, 90 triangle right there. And if this whole side is S, this is 1/2 S, or S over 2. Meaning this height right here that we're looking for is S root 3 over 2. So S root 3 over 2. All right, so now I have the base and the height of this triangle. So I'm going to use a base of S, and then the height is S root 3 over 2. I'm going to plug these in to my area formula right there for a triangle and see if I can get a formula for the area of an equilateral triangle with just that S for the side length. So at the area equals 1/2 S times S root 3 over 2. And now we can go ahead and clean this up. The area is going to be s squared root 3 over 4. Or the square root of 3 divided by 4 times the side length squared. And this is for all equilateral triangles. So a real easy way to find the area of any equilateral triangle. All right, the next section, we do have a formula for the area of any regular polygon. Area equals 1/2 apothem times perimeter. So I can easily find the perimeter of a regular polygon if I have the side length. I just take the side length and multiply it by the number of sides. And the apothem, if I'm given, I can just multiply that by the perimeter divided by 2. So for this one, right here, we already found the apothem in the last problem. And we calculated the area using equilateral triangles. Let's see how that shakes out if now I use my area of a regular polygon formula. So I have area equals 1/2 apothem times perimeter. My apothem is 4 root 3. And now my perimeter is going to be the number of sides, 6 times the side length, 48. My perimeter is 48. Now I can simply plug these in there and there. Find the area. Area equals 1/2 4 root 3 times 48. Area is 2 root 3 times 48. Multiply that 1/2 times the 4. So our area is, just like we found using equilateral triangles, 96 root 3 inches squared. And when possible, leave it in the simplest radical form. It's the most accurate way. But we can use a calculator to estimate the area. And I get 166.3 inches squared. I'd like you to take a few minutes and try example 3 using the formula for the area of a regular polygon. So see if you can do that one, and we'll go over the answer in just a second. All right, let's see how we did. So we need 2 things. We need the apothem. Hey, we're given the apothem. That's nice. We don't need to solve for anything. And then we need the perimeter. I'm given the side length of 11.6. And then how many sides are in a pentagon? 5. 11.6 times 5. Give me the perimeter of 58. And then I just plug both those in. Area equals 1/2 times 8 times 58. Area equals 4 times 58. Area is 232, and we have centimeters squared. So real easy if I'm given a side length and the apostrophe. And oftentimes we're going to have to solve this. Moving on to our next example. If the side of a regular polygon is reduced to half its length, how does the perimeter change? Right? So in 10.4, we already looked at this, right? Let's do a quick example using some numbers. So here we have a scale factor of 4 to 2, which is 2 to 1. There's our scale factor. Now let's see the ratio of the perimeters. This one has a perimeter of 5 times 4, or 20. This one has a perimeter of 5 times 2, or 10. So the ratio of the perimeters, 3 over 10. Also, 2 to 1. So just reinforcing what we looked at in 10.4, the ratio of corresponding sides of similar polygons is going to be the same as the ratio of their perimeters. And we know the ratio of the areas is that scale factor squared. All right, so now we have our equilateral triangle. I'm going to find the area if I have an apothem of 14. All right. So now I'm just given this right here, this little baby part of the triangle. So my apothem is 14. And remember, if I want to use that formula for a regular polygon, what I need to do is figure out the side length so I can therefore calculate the perimeter. So this triangle right here is also a 30, 60, 90 triangle. So that's 30. And then there's our 60 right there. Right? We know our central angle, right, is 360 divided by 3. Or 120 degrees, and that apothem is going to bisect it. So that's going to be 60, 30, 90. So which side do I have? I have the short leg. We looked at our special right triangle before. So what's the radius? We don't need the radius, but the radius is going to be 28. And what's this? Half a side is going to be 14 square root 3. So 14 square root 3 is half of a side. So this entire side is 2 times that, or 28 root 3. So I have my apothem of 14. And then my perimeter is going to be 3 times 28 square root 3. So using special right triangles. So our perimeter of 84 root 3. Plug that in there. There's our apothem. So my area. 1/2 14 times 84 root 3. Give me a second to catch up a little bit. So half of 14 is 7. 7 times 84 root 3. I have an area of 588 root 3 centimeters squared, or approximately 1,000 and 18.4 centimeters squared. Questions on that? A little bit tricky. Just making sure we know how to use special right triangles. And as I told you in chapter 8, these come up over and over again. So the last example, we want to find the area of a square with a radius of 4. So remember what our radius is from the center to the side. I want to discuss a couple of different ways, 3 different ways to find the area of a square. Since a square is a parallelogram, we can do base times height. So the area, since the base and the height of a square are the same, is just the side length squared. We also know that a square is in fact a rhombus. So the area of a rhombus is 1/2 diagonal 1 times diagonal 2. And in the square, since those diagonals are congruent, area is 1/2 the diagonal square. Right? So that's another way to find the area of a square. And since a square is in fact a regular polygon, we can use the area is 1/2 the apothem times the perimeter as well. So 3 different ways to find the area of that square. Right? So now I'm given the radius of 4. I don't have the side length. So if I'm given the radius, the easiest way to go about finding the area would be this second method. If I extended this diagonal at 4, so the diagonal is 8. So the area is 1/2 8 squared. Area is 1/2 of 64. The area is going to be 32 inches squared. Well, that's not as much fun, right? Let's go ahead and calculate it using the other 2 methods as well. So now let's go about finding what a side length is. So the side length I'm going to go ahead and create my apothem, my bisector, and then we can find 1/2 of the side length here and 1/2 of the side length here. The type of triangle I just created there, though, is another special right triangle. That's our 45, 45, 90 triangle. Right? So this right here is 90 degrees. 1/2 of 90 is 45. That's 45. So this is an isosceles right triangle. Remember our 45, 45, 90 triangle? Where we have x, and then x root. And remember what we said. If I have that x root 2 side, the hypotenuse, I can go ahead and divide it by 2 and multiply by the square root of 2 to find the 2 sides. So both of those are 2 square root. So an entire side length would be twice that. So our entire side length here, 2 root 2 plus 2 root 2, or 2 root 2 times 2, is 4 root 2. So now I have a side length of a square, and I could use this method here, 4 root 2 squared. Remember how those exponents work? We're going to square the 4. Those are both to the first power. Remember, raising the power to a power, we multiply those. So we end up with 4 squared, which is 16. And the square root of 2 squared, which is just 2. For our area, again, should be no surprise, 32 inches squared. And then the last one, I want to use 1/2 apothem times perimeter. So the apothem, same as that half aside, 2 root 2. And now our perimeter. We have a side length of 4 root 2, and there's 4 sides. So 4 times 4 root 2 will give me the perimeter. So I end up with a perimeter of 16 root 2. And then I'm going to simply plug that in there, and that in for my perimeter. And hopefully I get 32 inches squared again. 1/2, 2 root 2, and 16 root 2. And so 1/2 of 2 is just 1, so those will go away. And I have 16 root 2 times the square root of 2. Root 2 times root 2 is square root of 4. Square root of 4 is just 2. 16 times 2. I end up with an area of 32 inches squared. So that's how to find the area of a square 3 different ways. I hope you enjoyed this tutorial. Please subscribe. Let's ring them bells.